Hey everyone, how's it going? Welcome. If you're ready to absolutely nail one of the most important chapters in KSSM chemistry, then you are in exactly the right place. We're going to break down everything you need to know about acids and alkalis. Let's do this. Okay, let's kick things off with a little puzzle for you. Think about this. What could lemons, soap, and jellyfish stings possibly have in common? I know, it's a pretty weird mix, right? But trust me, the answer is all about chemistry, and by the end of this, you'll know exactly what it is.
So, here's our plan for today. First, we'll cover the basics of acids and alkalis all around us. Then, we'll put on our lab coats and see how to identify them and measure their strength. After that, we hit the main event, neutralisation. Then we'll see why all this matters in your daily life, and we'll wrap it all up with some super useful exam tips to help you score that A.
All right, Section 1, Acids and Alkalis Around Us. Let's jump right in and get to know the basics. So what exactly are these things? Well, it all starts with the name. The word acid actually comes from a Latin word that means sour. That's no surprise, right? It explains why things like vinegar and lime juice have that sharp, sour taste. On the other hand, alkali comes from an Arabic word for plant ashes. And alkalis, they taste bitter and feel kind of slippery or soapy to the touch. Think about soap or even baking soda. You probably have both acids and alkalis in your kitchen right now. Okay, let's move on to Section 2, Identifying and Measuring Strength. This is where we get into the really cool lab stuff. Let's open up the chemist's toolkit. So how do we tell them apart in the lab? Well, first up is pH value. Acids are always less than 7, and alkalis are more than 7. Then there's the famous litmus paper test. Here's a super easy way to remember it. Acid has a D in it, and it turns blue litmus paper red. Simple, right? Alkalis do the opposite. They turn red litmus blue. And here's another key difference to remember. Only acids will react with metals to produce hydrogen gas. Now listen up, because this is a super important point, and it's a classic exam trap. All those properties we just talked about, they only work when the acid or alkali is dissolved in water. Without water, they're kind of asleep. So if you take a piece of dry litmus paper and touch it to some solid citric acid powder, guess what happens? Absolutely nothing. You need water to wake them up and unlock their chemical properties. Don't forget that. Litmus paper is great, but we've got other tools too. We use special chemicals called indicators. Think of them like chemical spies that change color to give us secret information. Phenolphthalein, for example, is fantastic for spotting alkalis because, bam, it turns this amazing bright pink. And then you have the boss of all indicators, the universal indicator. It gives you a whole rainbow of colors to tell you not just if it's an acid or alkali, but how strong it is. And that rainbow of colors leads us straight to this, the pH scale. You see, it's not enough to just know something is an acid. We need to know how acidic it is. Is it just a little sour like a fizzy drink? Or is it something seriously strong? The pH scale, which runs from 0 to 14, is exactly the tool we use for that. The rule is pretty simple. The lower the pH number, the stronger the acid. But here's a pro tip that many people miss. The scale is logarithmic. That just means that every single step down is a 10 times jump in strength. So a pH of 1 is 10 times more acidic than a pH of 2, and 100 times more acidic than pH 3. That's a huge difference. On the other end, the higher the number, the stronger the alkali. Something like sodium hydroxide at pH 14 is a really powerful alkali. So we have strong acids way down at the bottom and strong alkalis way up at the top. What's right in the middle? That's pH 7. This is our magic number, our perfect balance point. It's totally neutral, not acidic, not alkaline. And the most famous example of something with a pH of 7 is, of course, pure water. Okay, time for Section 3, and this is where it gets really exciting. This is the main event, neutralization. It's what happens when these two opposites finally meet. So what is neutralization? Well, it's exactly what it sounds like. You take an acid and you take an alkali, you mix them together, and they literally cancel each other out. The acid isn't sour anymore, the alkali isn't soapy anymore, they're both neutralized. And in their place, you get two totally new and neutral substances, a salt and good old water. Now, in the lab, we do this very precisely using a method called titration. I know, it might look a little complicated with all the equipment, but the idea is actually very simple. You just add the acid drop by drop by drop to the alkali, which has an indicator in it. You keep swirling, and the very second the indicator changes color and stays that way, that's called the end point. And bam, you stop. You've achieved perfect neutralization.
Okay, exam alert. You absolutely have to know your word equations. But don't worry, there's a really easy pattern to remember. Just look at the name of the acid. Hydrochloric acid will always make a chloride salt. Sulfuric acid will always make a sulfate salt. And nitric acid? You guessed it, it makes a nitrate salt. See, the question gives you the answer. It's a massive clue for your exams.
Right, let's move on to section 4, chemistry in your daily life. You might be wondering, okay, that's cool lab stuff, but why does this matter to me? Well, you're about to see that neutralization is happening all around you, every single day. Let's start with this morning. You brushed your teeth, right? Well, you were doing a chemistry experiment. You see, after you eat, bacteria in your mouth produce acid, and that acid attacks your teeth, causing decay. But your toothpaste is alkaline, so when you brush, you are literally performing a neutralization reaction in your own mouth to protect your teeth. And it's not just in the bathroom. It's out in the fields helping to grow our food. Sometimes soil can become too acidic, and crops just won't grow well. So what do farmers do? They add an alkali, like slaked lime, to the soil. This neutralizes the extra acid and creates the perfect, healthy environment for plants to thrive. How about your laundry? Ever wonder why clothes feel so much nicer after using fabric softener? Well, washing detergents are usually alkaline. They do a great job cleaning, but they can leave clothes feeling a bit stiff. Fabric softener is actually slightly acidic. So it neutralizes any leftover alkaline residue, leaving your clothes feeling soft and comfy. And here we are, the final and maybe most important section, exam quick tips. This is your key to absolutely acing that test, so listen closely. Okay, here is a classic KBAATS or HOTS question. Picture this. You're at the beach and someone gets stung by a jellyfish. Ouch. Now, jellyfish venom is alkaline, so what do? Well, you know about neutralization. You need an acid. Something like vinegar or even pineapple juice would work to neutralize the venom and ease the pain. But what should you never use? Soap. Why? Because soap is also alkaline. Using it would just make the sting feel so much worse. And that's a wrap on our quick guide to acids and alkalis. So I'm going to leave you with this final thought. Now that you understand the science of neutralization, start looking for it. Where else in the world around you can you spot this incredible chemical balancing act? I promise, once you start looking, you'll see chemistry absolutely everywhere. Thanks for tuning in and all the very best with your studies. You can do this.